It's a great pleasure to introduce today's speakers, Professor Dusa McDuff from Barnard College. She will be talking about embedding questions in symplectic geometry.
Well, it's a great pleasure to be here again. I'm going to talk about embedding questions in symplectic geometry, and I think I've talked about this here before, so I hope it won't be too repetitious. I thought I'd try and give talk about slightly different aspects of the subject though this time. And you know, the subject, I haven't actually been thinking about this incredibly recently, but the subject is still alive because today on the archive there were two papers, one of them absolutely about this and one of them sort of very closely related to these kind of questions. So, you know, there are things that people are still working on and thinking about. And some rather interesting questions that I hope to explain to you. But I think I need to begin by reminding you about what symplectic geometry is. So, since it's meant to be a very elementary talk, please do ask questions if there are things you'd like me to explain more. So, I'm going to be talking about symplectic manifolds, which are even-dimensional manifolds with a symplectic structure which is a closed two-form, which is non-degenerate. Which means that if you take it and raise it to its nth power, you get it never vanishes. It's a volume. And we're sort of interested in the geometry of this structure. We're looking at diffeomorphisms, for example, which preserve the symplectic form. They're called symplectomorphisms. So that's a diffeomorphism. Phi preserves symplectic form. Now, the immediate examples are, say, Euclidean space with its standard form, which one can write as, say, dx1 wedge dy1, that's up to different pairs, dxn wedge dyn. That's the standard symplectic form on Euclidean space. And one of the features of symplectic geometry is there are lots and lots of symplectomorphisms. I'll explain how you construct them in just a minute. But that means then that every symplectic form enters locally diffeomorphic, symplectomorphic to the Euclidean space. So you don't have all symplectic manifolds locally look the same, and so any invariants there are sort of global invariants that people try and understand. Now, symplectic geometry I find very interesting, partly because it's connected to complex geometry, and it's also connected to dynamics. So the connection with complex or Kahler geometry is that if you have a Kahler manifold, so a Kahler manifold is a manifold with a complex structure, and then it's got a Riemannian metric on it, and the metric I'm writing a complex structure in this slightly, perhaps non-standard way, but I think of J as an automorphism of the tangent bundle, which is equivalent to multiplying by I, so J squared is minus the identity. And on a complex manifold, this comes because the local transition diffeomorphisms preserve a complex structure, so you naturally get complex structures on the tangent bundle, and that's called an integral complex structure, almost complex structure becomes this way. You have a Riemannian metric, and in a Kahler manifold, one thing is to say that this J is parallel with respect to the Levi-Chipton connection or whatever. There are different conditions of the Kahler condition, but one way of saying the Kahler condition is that if you take the form omega, which is just given from G by taking it to the Hermitian part, doing that, this anti-symmetrizes it, then this is closed.
You also have to assume it's J invariant.
You have to assume it's J invariant, right. So this Riemannian metric is J invariant.
And J is integral.
Yeah, I said J is integral. So complex nonsense.
Right, but since I only wrote down the definition of almost complex.
Right, well I said this, I didn't write it down. I did say it. Okay, fine. That's now a correct definition of the Kahler manifold. But you see, every Kahler manifold with a natural, it's obviously non-degenerate, so you have a natural symplectic structure. And of course, it doesn't go the other way. If you start off with M and omega, you can't necessarily go to J, Though actually for a long time people didn't really know that. I mean, they didn't have examples where there was a Kahler assessment manifold, which was a non-simply connected manifold, which was symplectic but not Kahler. And then I constructed a simply connected version of that. But for a long time people didn't know the difference. But now there are lots and lots of known examples of symplectic manifolds which aren't Kahler. But what you can get an almost complex structure, which is a J like this, that lives on the level of the tangent bundle. It turns it into a complex vector bundle, and you can arrange that this is compatible with omega, so that this formula gives you a metric. So you can arrange that omega J, J, W is omega W, and that G, which is that if you take up omega, JB, that's always positive. So this implies GJ is metric. So you get a sort of almost Kahler manifold which has a triple like this, but it's the J is not equal. Now, of course, one of the interesting questions to me is how much do you lose if you don't have an integrable J? I mean, obviously you get a much bigger class of manifolds which are symplectic rather than Kahler, but sometimes the structures are very different in the Kahler case, and sometimes there's remarkable similarities. So, as an example of difference, there's a result of Grommet which says that pi 1 of a symplectic full manifold can be any finitely presented group. And if you know anything about Kahler manifolds, you know that's absolutely not true for Kahler manifolds. So, for example, you've got to have pi 1 so that the H1 has got to, its abelianization has got to have even rank, for example. So that's a case where you have structure in the Kahler case and it disappears in the symplectic. And there certainly are cases, I'll give you more kinds of cases, where you have structure, not necessarily in the Kahler case, but you have structure which is there in the symplectic case and then disappears at some point. But then there are other cases which perhaps we'll meet with later, where there's structure in the Kahler case which actually you see in the symplectic case. So I mean, you don't lose everything. So that's a little bit of introduction to the relation with complex geometry, and then the relation with dynamics, is that the relation really is that on the symplectic manifold you have lots of symplectomorphisms, and it's easy to construct symplectomorphisms which are isotopic to the identity, because you can just take a function on the manifold. And so that's just any old function, smooth function. Then take what's called its symplectic gradient, which is a vector field, which is defined by the identity that if you pair it with omega, that's a one form, and that's meant to be equal to dx. So it's just like the usual gradient, except that you use the symplectic form as a pairing instead of the inner product as a pairing. And it has the property, and it's sort of different from the ordinary gradient, is that this is h equals constant, and then sort of dh, of course, the tangent space here is the kernel of dh. Right, so dh is sort of pointing the dual vector, but orthogonal. Now, of course, if you take the standard gradient, it's going to point in that direction. But the symplectic gradient is actually tangent to the level set. And that's because of the skew symmetry. You see, if you take omega of xh v, that's dh of v, which is 0 if v is tangent to the level set. Right. So it's in some ways it's sort of like the ordinary gradient, but in other ways it's just the properties are completely different because it's tangent to the level set. And in fact, if you integrate, if you look at the flow of xh, it's actually it preserves omega. So you get lots of symplectomorphisms this way. I mean, these are symplectomorphisms that actually obviously preserve the level sets of this function, But you can get more general ones by allowing H to depend on time. And then you get something where there isn't a level set now because H is changing with time, but you can still integrate and get another one kind of a group, but you can integrate and get a path of diffeomorphisms, and that's still preserved. So that gives you, well, if your manifold is simply connected, that gives you all the symplectic morphisms isotopic to the identity. It gives you a large amount of symplectic morphisms. In general, this set of things is what's called the Hamiltonian group.
What's the kind of compact things?
Yeah, and it's close. So you can actually integrate that. Otherwise, you have to say things infinite. Yes. Okay, so then there are a lot of interesting dynamical questions, but I'm not really going to talk about those so much. I mean, I know there are lots of people interested in dynamics, but I wasn't going to talk about those. But what I was going to talk about more was questions of look at symplectic morphisms and see what they do to subsets of the manifold. So that's what a symplectic embedding question is. You take a target, you take a domain, which would be a sort of standard domain, which would be like a ball. So I'm going to take a ball. This is sitting inside Euclidean space, standard Euclidean space, and normally one takes the radius of the ball, but I'm going to take A to be pi r squared. So that's sort of the symplectic area. So if you've got a ball, this is a ball whose radius is such that if you look at the two-dimensional slice in, say, the x1, y1 plane, then the area of that is A. Because that's a natural symplectic measurement of it. It's a symplectic area of something. And in fact, if you just take a ball, you see the boundary of the ball is the level set of the sum of xi squared plus yi squared is equal to a constant. And if you look, so that's a function h, and if you look at the corresponding symplectic gradient xh, you can just calculate, that's just rotation. It's just rotation, it's diagonal action. Its orbits are just, e to the I theta z, well, x1 plus pi y1, and so on. You just multiply by. You think of it as Cm. It's just multiplying by e to the I theta. That's a diagonal circle action. And so, this boundary of this disk here is an orbit of that flow. And what we're taking as a measure is just a disk, the symplectic area of the disk. That's what's called the action of that orbit. Anyway, so that's one test, obvious, simplest kind of test domain. You can take ellipses, or ellipsoids, which are very similar. They've been characterized by numbers EA1 up to AN, where you'd be taking the sum of xj squared plus yj squared over aj less than or equal to 1. And so this would be just like a ball, except it wouldn't quite be so round. And it would look like this, having one thing like that and another one like that. So that's another kind of thing you could take. And another thing that people look at is the next easiest thing is what's called a polydisk, which is just the product of two-dimensional disks. So this is more like a sort of square shape. So you can take these test domains, and then you can ask, given a manifold, can you embed your test domain into your manifold? So you can look at the embedding space, symplectic embedding, say, of one of your test domains, like B2N A, into the manifold anyway. And the question is, well, is there anything interesting you could say about this? And of course, those of you who had me lecture about this before know that the fundamental result in this area is Grommet's non-squeezing theorem. Which tells you And then this is why people started looking at these embedding questions and why we have some knowledge about them. Tell me, if you start with a ball of size A and you try and embed it symplectically into a sort of polydisk of B2A, say, times Euclidean space, with a product form, so this would be sort of x1, y1, and this would be all the other variables, then his claim is that there exists a symplectic embedding of this kind if and only if little a is smaller than bigger, so that all you can really do is just put the thing in linearly. There's no way of taking a round ball, a big round ball, and sort of massaging it so it fits inside the lump. You can't squeeze it. You can't. It tells you that there's this ball which has got some intrinsic size that just can't be put into a system. And this was a theorem that he proved in 1985, and in it he inaugurated his theory of J-homomorphic curves. So you look at these sort of almost complex structure in your manifold, and you can't do all that much geometry with these almost complex structures, except in the case if you can use the fact that if you have a two-dimensional surface with an almost complex structure on it, then in 2 dimensions it's always integral. And so that means then that if you have two-dimensional J-homomorphic submanifolds, they're actually images of Riemann surfaces. And because the Cauchy-Riemann equation is it's a Fredholm equation, it means that you get a nice theory of what's called J-homomorphic curves. So there are two-dimensional objects in a manifold like this whose tangent spaces are J and A. And so you can use that theory. I might have time to explain a little bit how to prove this theorem. And this theorem, then, once you have that, you can define what's called the Grommet capacity of some manifold, which is the supremum of the size of the A's, such that there is a symplectic embedding into your manifold. And so that is a sort of interesting number. It's obviously a symplectic invariant. It's always positive because of Darboux theorem, so locally every point has a neighborhood which looks like standard Euclidean space, so you can always put in some little ball. So it's always positive. And actually there are remarkably few cases where we can actually calculate it. I mean, it's a sort of obvious question, what is it? But it's not known. It's calculated in only a few cases. And you might think, okay, this is a slightly obscure symplectic invariant, why would you be interested in it? But in fact, this CG is what's called a symplectic capacity. It is a symplectic invariant. And it has a property that if you have phi as a diffeomorphism of Euclidean space that preserves such that the capacity of U in standard Euclidean space is the same as the capacity of phi U for all U, little o to U, say. Then phi is a symplectic morphism. I suppose I want it to be orientation preserving. So that's really a remarkable thing. So this is an invariant which is really, we're looking at comparing, we've got some open set U, and then we're looking at what phi does to it. And we're saying that just the size of how big a ball you can put in here determines if always the capacities of these two sets are the same, then phi is a symplectic morphism. And it is a remarkable theorem because to say it's a symplectic morphism is saying something about the derivative of phi. It's saying that the derivative preserves a symplectic form. But here we don't have any mention about derivatives. This is just statement.
Phi is a homeomorphism?
Well, I'm assuming it's smooth. Because yeah, I mean, you can make a definition. You could look at homeomorphisms which have this property, and then you call them symplectic homeomorphisms. And you can try and understand them, but it's actually quite hard to understand them. I mean, nobody's proved anything terribly interesting about them. I mean, people have said things. But what you can do here, what this implies is that, for example, if you have phi n, which converges to phi uniform, phi infinity, say, uniformly, and suppose you're looking, so on some set, some compact set or something, you've got a uniform convergence, so that just means C0 convergence. If the images converge, and if these are phi n symplectomorphisms, that implies that phi infinity is symplectomorphism. So it tells you that the symplectomorphism group is invariant under, I mean, when you close it among the diffeomorphisms, so I'm assuming this is a diffeomorphism, that it's C0 closed in the diffeomorphism. So it's telling you that symplectic geometry is very robust, in a way, because the symplectic property doesn't really depend on the C1 convergence. It's okay for C0. So in a way, that's the beginning of symplectic topology. It's telling you it's some sense of topological subject, rather than a sort of geometric. I mean, it's why we have symplectic topology rather than symplectic geometry. Why we use both words. Because, so this is telling you a very robust property of symplectomorphism. And then, of course, there are lots of interesting questions about if you have certain properties of symplectomorphisms, to what extent are they preserved on the C0 limits? And so, not very well understood. Anyway, that's by way of introduction. So, what I thought I'd do is, I mean, I don't want to tell you all the detailed results that are known about this kind of symplectic embedding and that kind of symplectic embedding. I thought I'd give you just some sample results and some questions that people can ask.
So this result about the preserving the capacity
right.
image, is it ever proved for a smaller class of subsets than all possible sets?
Yeah, I mean, you can ask that it's true if you as a ball, just on balls, and then for all balls.
And is it still true? This fact.
Yeah. I mean, the basic idea is that
presumably it's not for neighborhood basis of any kind, right?
probably for.
Because you just shrink to.
Well, what you really want to know is that you really need to have a class which is invariant under rescaling. It's sort of homothet. Because what you're doing is saying that if you're trying to differentiate at a point, say you're differentiating at the origin, what you're doing is multiplying phi by a homothet and taking a limit. And if this is closed under homotheties, and this is true, then the derivative is going to sort of have the analogous property, a sort of linear version of this, where you have a ball here and you have some kind of symplectic ellipsoid on the other side. And then you just prove that that sort of affine non-squeezing property actually characterizes symplectic linear maps among all linear maps. It's not totally obvious, but it's not a deep result that this capacity preserving gives you, tells you that you have this anything preserving capacity is a diffeomorphism. What is a deep result is to show that you can sort of use any capacity here. It doesn't have to be this one. This is Grommet's capacity, which is about embedding balls. And there are plenty of others that people have about measuring, on the boundary of the set, you look at all the closed orbits. It doesn't always have closed orbits, but say if it's a convex set, it always has closed orbits. And you pick out the action of the smallest closed orbit for a convex set. That would be a capacity. So that's the kind of thing that Hofer did. So, I mean, there are different ways of defining. There are many, I mean, that's an interesting question. It's right. What capacities are there? And actually, there's one conjecture. Is it true that for convex subsets of Euclidean space, all capacities are the same? Actually, no, that's yeah, I think that's a true conjecture. It's not known that they're all the same. I mean, if there's a convex subset of Euclidean space, then I mean, you have some action. It's meant to be an invariant, and it's also meant to have the property that the capacity of the ball here is meant to be the same as the capacity of the cylinder. So you have that hypothesis. And then I think it's unknown whether all capacity is the same for the complex set. Anyway, so I was going to. So let's see. So perhaps I should start off with some questions. So one question I rather like, and I don't think anybody has any idea of how to prove it, but gives you an idea of what people might ask. What if you have a manifold with an integral symplectic form? Then the question is the Grommet capacity bigger than equal to 1? So can you put a large ball in it? I think that's unknown, and I think that nobody knows how to prove it. It's a sort of nice question. So now, another question is every four manifold fully filled, actually very fully filled, by an ellipse? So what that means, so I was talking about ellipsoids over here, and I gave you, I mean, now obviously the basic definition is you take some quadratic form, positive definite quadratic form, and you look at where it's less than or equal to 1. But you can show that there's always a symplectic linear transformation that makes it sort of diagonalize the symplectic form. So you could, the quadratic form. So you can always assume your ellipsoid looks like this. And so, you have a pair of numbers, an ellipsoid AB. And to say it's very fully filled by an ellipsoid would mean that you have does there exist an AB such that if you take the interior of the ellipsoid, AB, and you map it into M4, that the volume of M4 minus the image of the ellipsoid is given. So you fill all the volume by the interior of one open ellipsoid. Now, you might wonder, why on earth would anybody think that could be true? Well, it's true if omega is rational. And the reason it's true if omega is rational is, I mean, this was an observation due to Upstein. The reason is that if you have a rational symplectic form, you can multiply, there exists a k, so that k omega is integral, and then but there's a k such that k omega is represented by, well, actually a J homomorphic, but a symplectic submanifold Q or D. I mean, this is a result of Donaldson, and this is one reason why we say this is one way in which symplectic manifolds are like complex manifolds. Because if you had a complex manifold with a rational form, you could embed it. You could put it into projective space or height, and then you put a hyperplane divisor and then intersect with a hyperplane divisor. So this is sort of like a hyperplane thing. And so once you've got the symplectic submanifold D, it's a codimension 2 bundle, right? Because this is a codimension. It's a codimension 2 class. So you've got this line number. And actually, Donaldson also proves that a disk bundle embeds. So in fact, the whole of if you look at, you've got this disk bundle over it. Well, to D. Disk bundle to D over to the speed of D. And this open disk bundle, you can choose it so E actually embeds into the manifold, and the image is everything. The image has zero volume. So the image is some kind of sort of Lagrangian, it's the complement M minus the interior of this thing is some sort of core on which the symplectic form vanishes. So there's a flow. You could take a little neighborhood of this and flow it and make it fill out the whole thing. So that's something basically due to Donaldson and perhaps Viran helped a little bit. And then the point what Opstein noticed is that if you take a D is after just a Riemann surface, right? Some Riemann surface, we're in dimension 4. So this is just a Riemann surface. So you've got a disk bundle over a Riemann surface where you can take the Riemann surface and take out some curve so it's just left with a disk. And if you have a disk bundle, so if you have this bundle here, E, and you restrict it to a disk, with this disk sitting inside the surface. This, symplectically, is an ellipse. Open ellipse. So you just, that's just a normal form theory for what the symplectic forms look like. We've got this vibration in 5 of the sort of symplectic lines, and it's a disk bundle, and you can just prove that it looks like an ellipse. And therefore that gives you an embedding into it. So it tells you that sort of, any rational symplectic manifold is, if you move a little bit, it's just an ellipse. So then, well, I have no idea whether this is true for irrational things. This is a paper, I just told you there was a paper put on the archive today by Dusa McDuff and Opstein. And what they proved, they formulated this conjecture there, but one of the things they proved was what's called packing stability for all closed, these are closed manifolds, closed, and for, and this is a slightly surprising result. When we start looking a bit more in detail about embedding balls into manifolds, if you have a manifold, you usually can't embed a ball into it. If we took, say, if we take this cylinder, suppose we took a disk times A times a disk of size 1, where A is less than 1, then the largest ball we can put inside here has got size A. So we're going to have something like that. We're going to have a ball. It's certainly not going to fill the whole thing, because it's constrained. But if you try and put in 10 disks, or 10 balls, then possibly you can fill the whole volume. And what packing stability means is that for every number, whether this is rational or not, there is some number m, so that m can be fully filled by k balls, k equal balls, for all k bigger than or equal to m. So to say it fully fills it, you can take k equal balls of the right size to fill out the whole volume, or perhaps all within epsilon of the volume of the total volume, any epsilon. So you can basically fill out the whole volume of this by k equal balls. And what's surprising here is that k is just any number bigger than n. So n might be like 100. But then for 100 and 101, 102, or however many balls you had, you could always fully fill it. So it means that the structure, if you look at the question, we have k equal balls, and can we fill the whole of the volume with those balls? That's a question which there are obstructions when k is small. But eventually there are no obstructions. And that's true now known for all 4 manifolds. So it's a case where whatever structure there is in the symplectic geometry question disappears when you weaken it enough.
So going back to the second question, if you tried to find an ellipsoid, just ask, can you find an ellipsoid that only misses epsilon volume for every epsilon? Is that true for every symplectic form? You'd think that maybe by just...
It's not known, because you see, if you think about this result, you're taking the symplectic form and multiplying it by k, where you have no control over this k. And then so that means that, if K is bigger, that means your surface here has got a lot of area. And it means your ball, your ellipsoid is getting thinner and thinner. It's getting very skinny because, the volume is sort of controlled. So as, the more irrational K is, omega is, the higher K is going to have to be. And so your ellipsoid is getting skinnier and skinnier. So there's no sort of obvious limiting argument.
Right. I was just hoping that you would get, just by now perturbing the form a very small amount, that you would get some mass.
Well, you can form a small amount and you can get some weird form on the then how do you perturb it back again?
So you then try to go onto a smaller ellipsoid, perhaps. And
these continuity arguments are very difficult. I don't think that they work. I think you have to, for this kind of thing, if you're trying to, you can't make that argument work very well. Anyway, I like this this kind of packing stability is a nice result because it gives an example of the kind of thing that happens in symplectic geometry where you have a question which has structure, and then you increase a parameter and the structure disappears. Anyway, so those are questions that people don't know the answer to. Now, there are lots of different things I could say. One thing, let's see, I was thinking of showing you, since I don't have all that much time, I'll talk about tori. Because you see, I've told you about the non-squeezing theorem, which is a theorem about embedding a ball into two-dimensional disk times 2m minus 2. And the way you prove this, it's hard to prove results when everything is non-compact. What you do is you compactify this, and you compactify it to 2 spheres by adding a point. And the idea is if you have a product like this, S2 times A, then if you take the product structure of J0 times JR, n minus 1, then in the product structure, you have a lot of spheres, because you have S2 going in as S2 times point. And they're sort of holomorphic spheres going in like that. You have one of those through every point, basically. And then the idea of what Grommet's theory tells you is that if you deform J, then you still have these spheres. These spheres persist because they're regular solutions to the Cauchy-Riemann equations. When you perturb the equation, you still have solutions. So, and then the existence, he shows that the existence, because you have a curve through every point, for every J, that somehow constrains the size of the ball you can invent. And that argument is actually quite beautiful. So perhaps I should just briefly explain that. Suppose you have a ball here. This is one of the arguments that works in every dimension. And you're mapping it into a cylinder. And so we take J0 here. Suppose we have an embedding. We argue by contradiction. Suppose we've got a large ball. We're mapping it into here.
Different J0.
Different J0. You look at a J on here, which equals the push forward of the standard J on the image of the ball. And then, so on here it's a push forward of the J0. And outside you just extend it to make it 10. So you can always do that. And then you look at the center point here, and the center point is there, goes to wherever it goes. And we have the deformation theory tells you that through this point you always have some curve here, C, which is the image of a two-sphere, and it's U is J homomorphic. So you always have a J homomorphic sphere through every point. So then we look at this bit of the curve here, the bit that sits in the image of the ball, and pull it back to here. And when we pull it back to here, it's a J0 holomorphic curve, or funny J0 holomorphic curve. Just because we just push forward that J. So we have a standard holomorphic curve in standard Euclidean space. And then, well, the way Grommet argues is that this is a minimal surface then. We're in the standard Euclidean space with the standard symplectic form, you have the standard metric. Any holomorphic curve, any holomorphic two-dimensional surface is actually a minimal surface. And then, so this is a minimal surface in Euclidean space going through the center. And therefore its area, with respect to the standard metric, has to be at least pi r squared of the radius and form, which is what I call n. So its area has to be at least n, because the smallest area of anything that goes through the center is just a flat center. That's absolutely area. So this has got to have bigger area. On the other hand, this G0 area of this surface, S, is in fact the same as the symplectic interval of the symplectic form on S. Because it's holomorphic, you can check that very easily. And so then the symplectic form on S, of course, is less than the symplectic form on C. And the symplectic form on C, well, by construction, it's in the class of this two thing, and that's A. So that tells you that little a is smaller than bigger. So it's a very beautiful geometric argument telling you that the existence of all these spheres, and they don't have to be spheres, they just have to be holomorphic curves at every point for every J, will constrain the size of all. And so that's a sort of general result. The more, if you have holomorphic curves to every point, then that constrains the ball. And the thing is that if you have spheres, you have lots of holomorphic curves. So now look and see what happens if you look at B2M A and you try and embed it in a torus. So by this, I just mean the torus with area n, right? So you just, and so this is n. So now if A is less than, if A is bigger than A, does there exist as embedding? And, you normally think, well, the torus and the sphere are sort of the same. On the other hand, if you're an analyst and you know about these equations, you know that the Cauchy-Riemann equation for tori is very different from the Cauchy-Riemann equation for spheres. And that, for example, if you look at T2 cross T2 with its product complex structure, this, of course, it has lots of curves in it. It has all the flat sides, it has all the constant curves. But if you slightly perturb this, they all disappear. They're just not there. They're not generic. If you look at the equation, it's got some kernel, and it's just not generic curves in it. So typically, for a standard J, so this perturbs to J, and these things will disappear. So there are no curves when you have a torus. Just that. And similarly here, there are lots of tori here, but you perturb J a little bit, there are no tori. So then if the yoga is that these curves are meant to detect the invariance, you should say that you should be able to embed this book. And in fact, there's a really easy argument to show you can embed the book, so I thought I'd explain it to you. This is something that Todorovic knows. That you can always embed it. However big B, D2N, A, and S. In, say, T21, R, 2N minus 1. Or. And so, the torus just doesn't constrain. And so you take manifolds that sort of look the same and they have radically different behavior. Now, I can explain that to you because that's very easy. It's based on a really simple argument. So we have a big ball, and we're trying to embed in the torus, say, size 1, across our end. So we're going to here have, think of this as R2 times R2n minus 2. And this is the R2 direction. And we're going to map this down then to R2 modulo by Z2. So we're going to, we've got the integer lattice in here. And then we're just going to take a sort of fundamental dimension. And the idea is to take this big ball and map it into here in such a way that when you look at its image here, it's really big ball, so it's going to look something big. This is not very, perhaps I should make my image a bit bigger. We're going to map it. This is going to be phi of the ball. And we're going to make each of these slices, if we take a linear map, this could be L. L is linear. And so, you know, all planes intersect this in circles. So this is going to intersect this in a family of circles. And all we need to know is say that the area of the circle of the intersection of L of the ball with these planes are 2 times point. You just need that say to be less than 1. And then it never contains more than one point of the integer lattice. Right. So, well, perhaps I should be safer and make it, well, anyway, whatever it has to be, small enough so it only can't go through more than one point of the integer lattice. So then you want to say, well, is there a linear map which takes this very solid-looking object to something which is sort of skinny ellipsoid, which intersects these things in small disks? And the thing is that what you need to do is to look at what, so these are this family of planes, V's, we call it, look at the one through the origin, that's the V through the origin. And look at what its inverse image has to be, L inverse of V. Well, L inverse of V is obviously some 2 planes through here. And it's got to intersect the ball. It intersects it in a large disk, obviously. The disk is of radius 1. But the symplectic area of that disk is meant to be small. So we would need to have this intersection. We want that intersect B2, the symplectic area of that. We want to be less than whatever we decided. What we decided to call it, whatever it is. We want it to be small. So we just need to find a 2-plane which is symplectic. So we want this, omega 0 restricted to L to be non-degenerate.
So this is a linear map that preserves the symplectic form.
It's a linear map. This is a linear map that preserves the symplectic form. And then I'm going to do this projection. Right? And so we look at symplectic linear maps. We want it to be non-degenerate. And then, you see, the point is that if you look at the 2 planes, if you look at R2M with its symplectic form, and you look at 2-dimensional subspaces of it, then that's a sort of Grassmannian here. It's absolutely not a homogeneous space, because there are 2-dimensional things on which the symplectic form vanishes, because you've got Lagrangian ones. It's just in the x1, x2 direction, for example. The form vanishes. If it's in the x1, y1 direction, the form is a standard area form. But because you just move it until it's symplectic, non-degenerate, but you can make this as small as you want. You can make this just by choosing the right plane. And then, so this is a symplectic plane, but this intersection has a small area. And then you use that the symplectic linear, in fact, is transitively on the plane. So there is a linear map that takes this plane to that plane. And of course it distorts things in the other direction, but that's okay. It's still going to have the property that all these parallel things are going to be the images of parallel things here, and they're all going to have the right intersection. And therefore, you could get this embedded. It's a very simple argument.
So the one through the origin has the maximum area, and the other ones?
Yeah, the other ones are small. What this seems to be saying. It's an ellipsoid, right? So this is sort of the biggest thing. But this is a very elegant argument you talk to rubbish. It just shows you that tori really do not squeeze. And it's not just, you don't need to do analysis to do that. You can just look at linear algebra to do that. So then,
I guess in terms of getting the intuition for it, the main point is that there are Lagrangian planes, and then you can find...
There are Lagrangian planes where the thing vanishes, and therefore the nearby are arbitrarily small. And therefore you can just distort it in this way. And, there are very few, this is one of the sort of emblematic embeddings you have that you might not expect. And this was dressed up by Gus to get a rather nice, interesting embedding of polydisks and polydisks. But in general, we have very few embedding techniques, and we don't know how to embed things. But, we have a few techniques, this is one of them.
Is this still true for hyogens?
Oh, yeah. It would be just the same. You just... Well, you have to adapt it slightly, but I'm sure it's true. You could just take, just take a, this is mapping one-to-one into this fundamental domain. So you just need to take this fundamental domain and put it into any Riemann surface. Just cover it, take the Riemann surface. Well, except it's wrapping around. Well, I'm sure it's true. I haven't done the details. That's a more honest answer. I would say definitely it's true. I haven't checked. That's honest, right? So you can check. Homework for you. So then the other thing I wanted to say, since I should finish, is recently I worked with Schlenk and Latcher, the student here, student Blaze here, myself, and we were actually trying to, because we really know very little about what the Grommet width is of various, what is this invariant? And we know what this invariant is for some four-dimensional manifolds, in particular for ruled manifolds, rational manifolds, and blow-ups, no blow-ups. But if you take T4, that's sort of the simplest manifold, which with a linear form, we were actually trying to calculate what the Grommet width is. How big a ball can you put in there? And what we found is that this is actually equal to, it's equal to, it's as big as it can be. So this is A, where the volume of the ball of size A is equal to the volume of this torus, whatever it is. The volume of the ball of size A, where I've done it in A squared over 2, the volume of the linear volume of the torus is whatever it is, you just know what the linear form you take. Anyway, you can basically fully fill it with a ball. And the interesting thing about this argument is that it divides into lots of cases. We started off by looking at sort of the square torus, which is T11, which is just R4 mod G4. We thought, well, this is a really simple manifold. We should be able to figure out what it is. This one turned out to be the hardest one. This one you actually have to do by hand. You have to construct an embedding by hand. All the other ones, it turned out you could do some little trick and use algebraic geometry and various things to figure this out. But just to end, if you look at this manifold is it has complex structures, and if you try and put a Kahler form, if you try and put a ball that is sort of consistent with a complex structure, then you can only fill for this the Sheshadri constant, which is what tells you sort of the fraction of the volume that can be filled by consistent with its complex structures. The Sheshadri constant is 4/3, which means that 8/9 of the volume can be filled. So in fact, in the symplectic case, whatever obstructions there are obstructions in the complex case because there are complex structures in here which have lots of curves, but they're not generic, so they disappear in the symplectic case. And so we don't see this in the symplectic case, so you can just fill as much of the volume as you want. But if you take T6111, for example, our explicit embedding techniques, we never did them in dimension 6. So I think it's really the symplectic geometrists should do something, because the algebraic geometrists get bounds which is better than we can get by embedding. Which really that shouldn't be. I mean, we should definitely do better than algebraic. It's a question of, it's slightly complicated thinking of these embeddings. And one thing that sort of is useful in a four-dimensional case is we do a sort of Lagrangian splitting. So we split a ball sort of in the Lagrangian splitting looks like a diamond across 0, 1 across 0, 1. So these are the y1, y2 coordinates, and these are the x1, x2 coordinates. So this is sort of a Lagrangian splitting. And, and then you want to try and map that into something which is sort of square. And because this is a rectangle, and you're trying to map it into a rectangle, you can actually do it. But if you're in 3 dimensions, the analog of this is an octagon, because it's a dual of the octahedron, because it's a dual of a cube. And then you're trying to map an octahedron into a cube, sort of fully fill a cube, by means of you have to be very careful with these maps when you do to make them. So you can do shears, you can do various kinds of things, but octahedra have different shape from cubes, so it's hard to see how to, and sort of at that point I spent so much time thinking about the four-dimensional case, I thought somebody else would deal with this. On the other hand, it's a nice question, in 6 dimensions it's completely explicit. You just need to have a good 3-dimensional imagination and sort of see how you can take this octahedron and shear it around and do things to it. Anyway, I'll stop here. Thank you.
So, going back to this filling problem,
Right.
when you have these rational classes,
Right.
I mean, you could try to find a divisor and then look at the line bundle and use kind of ignore the exponential map to push out the disks.
Right.
What do you do when it's irrational? I mean, you're
Well,
not close to irrational.
Yeah, what I've shown though is that you see, this was using a Donaldson divisor, which was a single divisor, which he took his symplectic form and thought of it as a linear combination of rational things, and then he took a more complicated, a divisor which had normal crossings.
I see.
And then he decomposed his manifold into pieces which were either ellipsoids or what he called sort of pseudo-balls. So they're things which are sort of like balls, but not quite like balls. So he just cut the manifold up into pieces and then showed you could adjust the sizes to improve it. I mean, So it was only using Donaldson's method, but it was you took a linear combination of divisors.
Any other questions? I have one question. So
Yeah.
your question 1, is there a uniform lower bound? No. You
Nothing is
obviously
nothing.
one.
I said one, but we don't even know it's silent, right?
But even when the case when, say, objective variety or something.
I don't know. I think nothing is known. Nothing is known to me.
Okay, before we kind of speak again, so there will be dinner tonight, and if you want to go, please talk to Mark, and let's sing it again.